Dear friends, welcome to this channel. In this video, I will discuss the questions from 76 to 100 in CUCET 2020 chemistry paper. Okay, let us take question number 76. A sample of pure S2-butanol was placed in a 10 centimeter polarimeter tube using the D line of a sodium lamp. The observed rotation at 20 degrees centigrade was alpha is equal to plus 104 degrees. The density of this compound is 0.312 gram ml inverse. What is the specific rotation of S2-butanol? Okay, this is the equation for specific rotation. Specific rotation alpha is equal to alpha by C into L. Here C is the density or concentration. Here C should be in gram per ml and L should be in decimeters. Okay, here alpha is given, alpha is equal to plus 104 degrees and C is given. Here C is 0.312 gram per ml and specific rotation, and this one length of the polarimeter tube is 10 centimeter. L is equal to 10.0 centimeter. We know that 10 centimeter is equal to 1 decimeter. So the length should be in decimeter. The length is 1 decimeter. When you substitute these values, alpha 104 divided by 0.312 into 1. So what is the value you will get? Nearly it will be 104 divided by 312 into 1000 you can write. So when you simplify this equation, you will get plus 333 degrees. So when you simplify, you will get this one. So what is the value? D is the correct option. The following molecules are enantiomers, diastereomers, constitutional isomers, or homomers. Okay, these are the structures which are given. This one is Newman projection formula and Fischer projection formula. You have to convert Newman projection formula into Fischer projection formula. So when you convert this one, you will get like this. So in this case, this circle, what are the substituents which are attached with circle? Methyl and bromine. So first you have to write this one, Me and Br. To this hydrogen is attached. So this is the hydrogen. And this carbon, to this carbon, this is this carbon. To this carbon, hydrogen and bromine are attached. So HBr. And what is the substrate? COOH. Okay, when you represent this one in Fischer projection formula like this, there is no change in relative configuration. And this can be written as, this one is equivalent to, you can write it as, okay, when you rotate this one, you will get COOH up and hydrogen down, and here there is a change of position. Here you will get Br, HBr will become BrH when you rotate this molecule, right? And here methyl bromine will become bromine methyl. Okay, here you have COOH, HBr, here you have BrH methyl. Then it can be converted into, at this center you have to convert it as a methyl should be at this axial position, at vertical position. Methyl should be at vertical position. Then only you can compare these two molecules. For this, at first center there is no change. You can put COOH, BRH, and in second center the methyl should be at vertical position. The horizontal methyl should be at vertical position. So when you change like this, okay, then there is no change in configuration. Without changing configuration, you can uh, change the position of methyl, hydrogen and bromine. So you will get methyl here and hydrogen here and bromine here. Okay, in this conversion there is no change in configuration at the stereo centers. Okay, finally this one is equivalent to this configuration. Here we know that if you take these two molecules, these are non-superimposable mirror images. These two are non-superimposable mirror images. Okay, when two molecules are non-superimposable mirror images, those are called as enantiomers. Diastereomers means non-superimposable, and these are not mirror images. Okay, these are not constitutional isomers, these are not structural isomers, they have same structure, and these are also not homomers. They don't have same stereochemistry. So, what is the correct option? A is the correct option. Which is the most stable conformation of ethylene glycol? Suppose if you take ethylene glycol, CH2, OH, and this is the CH2, OH. Generally, if you take this one, configurations, this is the carbon, and for this OH and two hydrogens, and to this carbon you have OH, hydrogen and hydrogen. Okay, this is the gauche, GAUCHE gauche, and you have another conformational isomer. Okay, all these are conformational isomers: anti, partially eclipsed, gauche, and fully eclipsed. Let us write all the conformations. Let us take OH, and here OH, hydrogen, 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 and hydrogen. These are anti. The dihedral angle is 180, opposite OH groups, and eclipsed. Let us take fully eclipsed. If you take here OH and OH, you have here hydrogen is eclipsed with hydrogen, hydrogen is eclipsed with hydrogen, and partially eclipsed, you have partially eclipsed, and here OH is eclipsed with hydrogen, and hydrogen is eclipsed with OH, let us take, and here H is eclipsed with hydrogen. Okay, which one is more stable? Generally, anti is more stable. Okay, when the group here in place of OH, if you write alkyl groups, generally anti is more stable, because in anti-conformational structure there is a least repulsion between these two groups. But here there is another factor which is responsible for the stability of this molecule. Suppose if you take gas, here minimum repulsions between OH and OH. Here there is a formation of hydrogen bond between OH and OH. In this case you have hydrogen bond, H bond you have, and less repulsions, less you can take steric repulsions, you can say. And in this case no H bond, that's why this one is unstable. Here you have H bond, but more steric repulsions. more steric repulsions. Okay, these repulsions destabilize the molecule. Here there is no H bond, no H bond. Still you have some repulsions. So due to H bond, the Gauss conformation is more stable and very less repulsions between OH group and OH group. The Gauss conformation is more stable. Suppose if you take fully eclipsed form. In this case also there is a hydrogen bond, but these repulsions between OH group and hydrogen, these dominates hydrogen bond. There is a little bit stability due to hydrogen bond, but this stability will be dominated by destability due to these repulsions, OH group repulsions and hydrogen repulsions. That's why the fully eclipsed form less stable when compared with Gauss. So in case of ethylene glycol, what is the more stable? Gauss is the more stable form. If you take N-butane, in that case, here CH3, here CH3, anti is more stable. Which of the following statement is not true according to conformational analysis of cyclohexane? Suppose if you take conformational isomers of cyclohexane, let us take, this is the energy. So these are the interconversion, CC bond interconversion. Let us take, here you can find this graph. Okay, symmetric. This one left side and right side symmetric. Here you have A, B, C, D, again C, B and A. Here A indicates chair form, less energy. This one also, this one, these two forms, interconversion of these two chair forms. And B indicates off chair, and this is the off chair. High energy state, least stable. This is the more stable. And next one is a twist boat. This is a twist boat. Twist boat structure. This one. Twist boat. This one is a twist boat. And this one is off chair. Off chair. This one is chair. And D1 is, what is a D? D is a boat. This is a boat structure we have. Here if you take stability order, which one is more stable? A is more stable, less energy, more stable. A is more stable, that is chair form is more stable. Next twist boat is more stable. Next boat, least stable is off chair. Why off chair is least stable? In the case of off chair, you have two CC bond complete or fully eclipsed CC bonds and two CC partially eclipsed CC bonds. That's why this one is highly unstable. When there is a eclipse between CC bonds, there is a repulsion between the bonding electrons. So that's why off chair form is very less stable. Suppose when there is an interconversion between two chair forms, suppose this is a and this is a B, when it is converted into this form, then this one will become B, this one will become, this one will become A, this one will become B. Means the axial position substrate will become equatorial, the equatorial position will become axial when there is an interconversion between two chair forms. Okay, let us take answers. When the two chair conformers interconvert, bonds that are equatorial in one chair conformer become axial in the other chair conformer and vice versa. This one is true. Okay, the transition state conformation is off chair. It does not contain any eclipsed CH bonds. Here you have eclipsed CH bonds, not CC, CH bonds. Sorry. eclipsed C CH bonds. That's why this one is highly unstable. The energy of twist board conformation is more than chair conformation. This is a twist board, this is a chair, so this one is more. The energy of a full board conformation is lower than half chair. This is a full board conformation, this is a half chair, this one is lower. So C is correct, D is correct, but B is not correct. Correct option, what is not true? Not true is B. So B is a correct option. Predict the major product obtained in the following reaction. Okay, acidic condition. So in this case, you will get OH, this one. You will get carbocation. So when you treat with H plus, so there is a protonation. First step, there is a protonation. So you will get OH2 plus, and there is a removal of water molecule. So next step, you will get carbocation. When there is a removal of water, you will get carbocation. It's a secondary carbocation. When there is a possibility of migration of methyl group, alkyl group, when there is a possibility of formation of more stable carbocation, that is tertiary carbocation, by rearrangement of methyl group or by migration of methyl group or alkyl group, then there is a migration. So when you migrate methyl group to this position, you will get more stable carbocation, that is tertiary carbocation. From this there is a removal of hydrogen. So simply you will get a more stable alkene, more substituted alkene you will get. So what is the correct option? D is the correct option. Which compound does not give a positive result in the Lassen's test for nitrogen? For Lassen's test, the organic molecule should have both carbon and nitrogen. Obviously, organic molecules have carbon. The organic molecule should have nitrogen. Then only there is a formation of Cn minus in presence of sodium. There is a formation of Cn minus. These Cn minus will be responsible for the test. So if you take aniline, it's a pH NH2. In this case, you have carbon and nitrogen. Glycerine, if you take, there is no nitrogen. So what is the formula of glycerine? You have CH2OH. It's a triol, OH and CH2OH. In this case, no hydrogen, no nitrogen. So it cannot exhibit Lassen's test. Benzamide, what is the formula of benzamide? PHCO NH2. It has nitrogen, so it can exhibit. Urea, NH2CO NH2. In this case, you have carbon and also nitrogen. That's why it exhibits Lassen's test. So what is the correct option? B is the correct option. The number of isoprene units are present in the sesquiterpene is. Okay, in isoprene, terpenoids, we have isoprene units. Based on number of isoprene units, you can classify terpenoids into monoterpenoids and diterpenoids and triterpenoids. And in case of monoterpenoid, the number of isoprene units. In mono, it is double. Actually, the name is mono, but how many isoprene units will be there? It will be 2. Di, it will be 4. Tri, it will be 6. Tetra, it will be 8. If you take tetra, it will be 8. And sesqui, if you take, it is in between mono and di. Sesqui, it has 3. Sester, if you take, it will be 5. So, how many units will be there in sesquiterpene? In sesquiterpene, you have 3 units. What is the correct option? C is the correct option. How many NMR signals the following compound exhibits are shown? Okay, number of NMR signals, this one is equal to number of non-equivalent protons. Non-equivalent, chemically non-equivalent protons. You have to identify number of non-equivalent protons. Okay, here CH3, okay, one type of proton. In this case, A, all CH3 groups are A type of protons. And here you have hydrogen. Here also you have hydrogen. By valency, you can easily predict. Here there is a hydrogen. So this hydrogen is B type. All these hydrogens are B type. And here you have 2 hydrogens. Okay, these are the C type. This one also C type, and this one also C type. So how many you have? You have 3 different protons. 3 different chemically different environment containing protons. So how many non-equivalent protons are there? 3 non-equivalent protons are there. So 3 signals will be there. What is the correct option? C is the correct option. The reactive intermediate involved in the following reaction is, okay, sodamide Na plus NH2 minus, it's a strong base. Okay, in this condition, what is the intermediate you will get? Okay, this is the reactant. This is given NH and this one. This is the bromine. In a strong basic condition, NH2 minus, this one abstract proton from this position. So, and here there is a removal of bromine, then you will get this intermediate. Okay, what is the intermediate? This one is benzene. You will get benzene intermediate. This is the benzene. And this one attacks on this center. So finally you will get this molecule after transfer of hydrogen to this position. You will get this molecule. So what is the intermediate which is involved in this reaction? Benzene or arine. Okay. This is the intermediate. So D is the correct option. Never rearrangement is conversion of. So in the case of never rearrangement, ketoxime tosylate directly converts into alpha amino ketones in presence of basic condition. And the ketoxime tosylate should have alpha hydrogen. Suppose if you take this, this is the tosylate NOTS tosylate. If you take, and this is the R, and this is the R, this is the alpha position. In presence of base OH minus, let us take. These are the acidic protons. So this one abstract proton. Here there is a generation of carbanion R, and this is OTS. This one is R. Sorry, ketoxime. So this one is N and OTS. OTS. Here this one attacks on the nitrogen. OTS is the best leaving group, so there is a removal of OTS, and there is a formation of third 3-member ring. So in this case you will get, this is the R, and you will get nitrogen, and this is the double bond. So after hydrolysis, here breaking of this bond, here there is addition of two hydrogens, here oxygen. So you will get and here you will get NH2, and here you will get C double bond O R. So this is alpha amino ketone. It's a base catalyzed reaction, and there should be alpha hydrogen. Okay, this is the reaction. So what is the correct option? D is the correct option. Which of the following compound is aromatic? For aromatic, the molecule should be cyclic, planar, okay, and also that should have 4n plus 2 pi electrons. Planar means all carbons should have sp2 hybridization. Suppose if you take this one 8 pi electrons, it's a 4n pi system. It's non-planar actually. Yeah, the shape of this molecule is tub shape. After tetraene, if you take, it's a tub shape. So obviously it will be non-aromatic. Suppose if you take this one is sp3 hybridized carbon. This carbon is sp3. It is also non-planar, so non-aromatic. It has 8 pi electrons. Usually all the carbons are sp2 hybridized. It's a planar molecule. 1, 2, 3, 4, 5. 5 pi bonds means 10 pi electrons. It's a 4n plus 2 pi system. That's why it's aromatic. And here there is a sp3 hybridized carbon. So it's obviously. Here there is another phenomena. It's a peculiar phenomena in this case. It's a homoaromaticity here. Here you have a homoaromaticity character. Here there is a delocalization of 6 pi electrons, and this sp3 hybridized this one will be above or below the plane. Here there is a delocalization of 6 pi electrons. It's a homoaromatic compound. So which one is aromatic? C1 is a aromatic compound. The stereochemical notations for the following compound is here G configuration, you have to identify RS. Suppose if you take double bond, this is the double bond. What are the substrains priority if you take? Suppose if you take these two, methyl group and COOH, obviously COOH gets first priority, and this one is methyl is second priority. And here you have hydrogen and COH group. So this one gets first priority, this one is second priority. Same priority opposite side. So what is the configuration? G is the configuration at this double bond. And if you take this one and this one, if you take OH, obviously hydrogen backside to the viewer. Here what is the numbering? OH gets first priority. Next one, this carbon and a double bond COOH. This side you have carbons, only single carbons. So this one gets second priority, this one third priority. So when you connect 1, 2, 3, what is the direction? The direction is clockwise. So what is the configuration? R is the configuration. So here R is the configuration. When you give numbering 1, 2, 3, 4. At second position Z and fourth position R. So A is the correct option. Sorry, at second position E. Okay. Sorry, not A. At second position, what is the configuration? E configuration. At the fourth position, what is the configuration? R. So this one is the correct option. So C is the correct option. 2E, 4R. C is the correct option. This one is not correct option. Identify the correct Fisher projection compound shown below. You have to identify correct Fisher projection formula. Okay, how can you write the correct Fisher projection formula? Okay, simply you can write like this in this. When this one is downside, this one is upside. When you write like this, these should be HCl and these should be ClH, and this is at vertical position, and this is also at vertical position, C2H5. Okay, this is the equivalent structure for this one. Okay, when you convert it into Fisher projection formula, you will get this type. This CH3 and C2H5 on vertical positions, and this one is left side, this one is right side, and this one is left side, and this one is right side. Okay, this is the conversion. Here CH3, HCl, ClH, first option correct, second one is wrong, third one also wrong, fourth one, suppose C2H5. Suppose when you rotate this molecule, upside you will get C2H5 and downside vertical position you will get CH3. So there is a change in position, HCl. It will be HCl and this one will be ClH. Okay, these are not equivalent. Okay, here ClH, HCl, these are not equivalent. So what is the correct Fisher projection formula? A is the correct Fisher projection formula. Predict the final product P obtained in the following reaction. If you take a thionyl chloride with hydroxy group, there is a SNI reaction. In SNI reaction, there is a retention of configuration. Okay, ROH will become, in presence of SOCl2, ROH become RCl at a stereo center, at a asymmetric center. There is a retention of configuration. So in OH position, you will get Cl with the same configuration, retention of configuration. So which one is the correct option? A is the correct option. Here there is a retention here, retention of configuration at OH. Here there is the inversion of configuration. Inversion. It is not correct. Here there is no SH, there is a Cl. This one also incorrect. So A is the correct option. The protein synthesis starts with the amino acid, namely. Okay, this one is methionine. Okay, if you take any protein synthesis, this one is started by methionine. First, there is a formation of methionine. After formation of methionine, remaining parts will be synthesized. Okay, A is the correct option here. The species that can be detected by mass spectrometer is, what are the species? Suppose if you take this one, let us take some parent molecule. Okay, when you send fast moving electrons, there is a sending of one electron, there is a release of two electrons. So you will get radical cation, free radical cation. You will get first there is a radical cation. Okay, this radical cation may be fragmented into small species M plus and Mi. M free radical. Okay, this one is the cation. Okay, which can be detected by spectrometer in case of mass spectrometer. Here this radical cation can be detected and cation can be detected. So only cations will be detected by spectrometer, and other anions or free radicals and neutral molecules, these cannot be detected. So what is the correct option? Cations are the correct option. Which compound gives a violet color with neutral ferric chloride solution? It's a very famous test for identification of phenol or phenolic derivatives. So phenol will coordinate with Fe3 3 plus, and there is a formation of complex. That complex is in violet color. What is Leucas reagent? A solution of sodium carbonate, sodium citrate and copper sulfates. It's a Benedict solution. This is used for the identification of aldehydes. Anhydrous ZnCl2 concentrated HCl. This is the correct option. Leucas reagent is anhydrous zinc chloride in concentrated HCl. 2,4-dinitrophenyl hydrogen. This one is used for the identification of carbonyl group, that is aldehyde ketone. And ammonical silver nitrate, it's a Tollens reagent. It is used for identification of aldehydes. So what is the correct option? Anhydrous ZnCl2 in concentrated HCl. Choose the correct structure of brufene. We know that brufene is a derivative of propionic acid. It's a derivative of propionic acid. It's a carboxylic acid. Here we have a propionic acid, and this is the derivative of propionic acid. It's ester. This is acyl chloride. It's amide. So all these are incorrect. This is the derivative of propionic acid. So this one is the correct option, 94. Predict the missing reagent in transformation shown below. Okay, what is the reagent? This is NaOH CHCl3 is a reagent. In this case, there is a formation of chlorination. There is a formation of chlorination. Suppose if you take NaOH CHCl3, okay, it's a Aromaticity type of reaction. In this case, CHCl3 plus NaOH, there is a generation of carbene intermediate, dichlorocarbene intermediate. This one is electrophile, electron deficient species. This one can act as a electrophile. So first there is a attack of these pi electrons. So you will get CCl2, and this one is double bond. These are lone pair electrons. So next step will be these electrons moves like this, these electrons move like this. So you will get, and here there is a removal of chlorine, CCl2. You can write 2 Cls, and here there is a removal of chlorine. So you will get this one. At this position there is a chlorine. So what is the reagent? NaOH CHCl3. It's a Aromaticity reaction of pyrrole. What is the multiplicity of methylene group in the proton NMR spectrum of butanone? Okay, butanone, let us take CH3, CH2, C double bond O, CH3. What is the methylene group? It's a methyl group. This is the methylene group. What is the spin multiplicity? Okay, when you apply n+1 rule. Okay, here how many protons are there? The CH2 group attached with CH3 and C double bond O. This CH3 has 3 protons. So how many, what is the multiplicity? The multiplicity will be equal to the number of protons on adjacent carbon plus 1. So it will be 3 plus 1. So what is the multiplicity? It will be quartet. Which reaction proceeds via following transition state? So in SN1 reaction, we know that there is a formation of, first there is a formation of carbocation. So first there is a formation of R plus. So if you take Rx, alkyl halide, there is a formation of carbocation and X minus, and there is a attack of nucleophile. In the second step, there is a attack of nucleophile and there is a formation of alkyl nucleophile substituted product. In SN2, there is a transition state between, Here, concerted mechanism, there is a transition state between X and nucleophile. Here, suppose if you take this one, this is a reaction center. This is a X containing carbon. Here there is no attack of nucleophile. Here there is the attacking of OH on hydrogen, which is adjacent to the CX bond. So, what is the mechanism? It should be elimination mechanism. In this case, here there is a formation of bond between hydrogen and base, and there is a breaking of bond between carbon and halogen takes place simultaneously. It's a concerted mechanism. Here there is no formation of carbocation, so G2 is the correct. In E1 case, there should be a formation of carbocation intermediate. Since there is no formation of carbocation intermediate, here you have transition state, so the reaction should be E2. What is the correct option? D is the correct option. Which of the following compounds does not undergo mutar rotation? For mutar rotation, the compound should be hemiacetal or hemiketal form, and also it should be reducing sugar. Reducing sugars exhibit mutar rotation. Okay, when there is a conversion of alpha anomers to beta anomer, when there is an equilibrium between alpha anomer and the beta anomer, when there is a disturbance of equilibrium between alpha anomer and beta anomer, then there is a change in specific rotation of the solution due to change in equilibrium position. That property is called as mutar rotation. For this, what is the condition? Okay, there should be hemiacetal or hemiketal form. Suppose in the case of monosaccharides, if you take monosaccharides, in monosaccharides case, the structure is hemiacetal or hemiketal. In case of sucrose, it's a disaccharide. In case of this, there is no hemiacetal or hemiketal form. This one has acetal form. So glucose, this one has hemiacetal or hemiacetal form. This one, fructose, has ribose. All these are monosaccharides. That's why these exhibit mutar rotation, but sucrose cannot exhibit mutar rotation. So what is the correct option? Sucrose is the correct option. C, sucrose cannot exhibit mutar rotation. Which of the following statements is not true regarding fatty acids? Okay, in fatty acids we have polar part, COOH, and also we have non-polar part, polar and non-polar part we have, and it's a non-polar in nature. Fatty acids dissolve in non-polar solvents. This one is correct. Triglycerides are esters of fatty acids. If you take fatty acids, it's a triglyceride. This one also correct. Most naturally occurring fatty acids have trans double bond. Actually, what is the double bond? Naturally occurring fatty acids have cis double bonds instead of trans. Fatty acids are biosynthesized from acetates. Okay, this one also correct. This one is incorrect. C is a correct option. Which of the following compounds does not give a tertiary alcohol upon the reaction with CH3MgBr? Okay, when you react with Grignard reagent, which one gives a tertiary alcohol? Okay, you can generate tertiary alcohol from ketones. Ketones are converted into tertiary alcohols, and also esters converted into tertiary alcohols. If you take aldehyde other than formaldehyde, aldehydes gives a secondary alcohol other than formaldehyde. If you take formaldehyde, HCO double bond H, there is a formation of primary alcohol. So you have to identify whether it is aldehyde or ketone or ester. Pentanol, it's a aldehyde. Aldehyde, it will give secondary alcohol. And ethyl benzoate, it's a ester. And this one give tertiary. And hexanone one, it's a ketone. So ketone obviously gives tertiary. And heptanone one, this one also gives tertiary alcohol. Which one cannot form tertiary alcohol? 3-methyl-pentanol. What is the correct option? A is the correct option. Since it's aldehyde, other than formaldehyde, gives a secondary alcohols. Thank you very much.